everybody, welcome to my YouTube channel Easy Mathematics. In my previous video, we come to know about how to find out a given sequence is convergent or not. In this video, we are going to find that if an infinite series is given, then how to verify that the given series is convergent, divergent or oscillatory. Actually, if we come to know how to find out the sequence is convergent, the same methodology we apply for the series also. But how we convert a series to the sequence form and how to verify its convergency and divergency, that we are going to search in this video. So first of all, what is infinite series, that we should come to know. So now if a1, a2, an be an infinite sequence of real numbers, then this summation is called the infinite series. Now we can form a new sequence by using this infinite series. So that new sequence, suppose it is S1, S2, S3. In this way we denote the sequence, where S1 is equals to A1, which is just the first term of the given series. Now S2 is equals to A1 plus A2, that is the first term plus second term. S3, that is the first term plus second term plus third term. In this way, if we proceed, then we can find out Sn, which is the summation of first n terms. This Sn is called the nth partial sum of the sequence An. So in this way, by constructing S1, S2, S3, Sn, in this way we can proceed up to infinity. So in this way, which sequence we form, that one is called the sequence of partial sum constructed from the given sequence An. So we will finally find out the sequence of this kind. After getting this sequence, now it is just like the sequence from the series, we just convert it to the sequence, where Sn basically the summation of first n terms. If we now take the limit of these first n terms, then it is going up to infinity. So that if we can able to calculate this part, then it is giving us the limiting value of Sn, which depicts that the given sequence is, that given series is convergent, divergent or oscillatory, depending upon the limiting value. So this limit Sn tends to infinity Sn. So this one is nothing but the sequence, and we know if that form we have, then for this one, if we want to test that it is a convergent sequence or not, we should find out that the limit exists or not. If the limit exists and it is finite and unique, then the sequence is convergent. Otherwise, it is divergent. Not only that, we have another procedure also. The procedure is, if we can show that the given sequence is monotonic, that is either monotonically increasing or decreasing, and it is bounded, then the given sequence is convergent. As S1, S2, S3 is forming a sequence, so for that sequence, we just apply the same form. After applying the same form, whatever the conclusion we will draw, that we can say about the corresponding given sequence, given series. So now, if limit n tends to infinity, Sn exists and is equals to S, then the series is convergent. Otherwise, a divergent series will be found. So let us verify this one with few examples. So the first example is, the given series is 1 cube plus 2 cube plus 3 cube. So this one is the infinite sequence. Here the Sn, the nth partial sum, is 1 cube plus 2 cube plus 3 cube, in this way up to n cube. We know the summation of this series is n into n plus 1 by 2 whole square. Its formula we know, and we derive in one video in the previously which we have done. Now, if we take the limit on both sides, then what we will find out? If we will take limit, then the limit n tends to infinity Sn is equals to, here it is 1 upon 4. That is from here, if we just take the 1 by 4 outside, then the limit of this part. So limit of this part is required. Now if we simplify this one and we will find out as n tends to infinity, then obviously this part is going towards infinity. So as this limiting value is going towards infinity, so that we can say the given sequence is divergent. Now one more example is here. In this example, the given series is 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 in this way. So now Sn is definitely, it is this one, and its last term is 1 upon 2 to the power n minus 1. As the first term is 1 by 2 to the power 0, we can say second term 1 by 2 to the power 1, third term 1 by 2 to the power 2, fourth term 1 by 2 cube in this way. So which is a GP series with common ratio 1 by 2. So that as it is a GP series and we know with n number of terms, so its summation is 1 minus 1 by 2 to the power n, as their total n number of terms are there, whole divided by 1 minus 1 by 2. Here we take this formula as the common ratio is 1 by 2, which is less than 1. Now if we simplify and take the limit on both sides, then what we will find out? We will find out that limit n tends to infinity Sn. For that, this limiting value for here 1 upon 2 to the power n minus 1, which we will find out, that one is infinity. So something divided by infinity is 0. So ultimately the limiting value is 2, which is a finite value, and we will get the unique value for this limit. So we can say the given series is convergent. Again, if we have one more example and just look the series very carefully here, the series is 1 plus 2 minus 3 plus 1 plus 2 minus 3, again plus 1 plus 2 minus 3, and it is going towards infinity. So just look at the series. This series, after each 3 term, it is repeating. So now here if we consider the Sn, so this Sn depending upon the n values will give us the different values. For if n is the multiple of 3, then we will find out all three terms we will find out all the times. So there in each bracket the summation is 0. So when n is equals to 3 multiple of 3, then the value is 0. When it is 3m plus 1, that means 3 multiple and 1 extra term, that means all such complete terms with 1 term extra, so that time the summation should be 1. And when it is 3m plus 2, and that time we will have the summation is here, it is 1 plus 2, not it is 2, it is 1 plus 2 is equals to 3. So that now if we take limit of this Sn, then that will provide us 0 or 1 or 2, 1 or 3 it is, depending upon the n values. So now Sn does not tend to a unique limit, though it is finite, but it is not unique. Hence we can say the given series is oscillatory. So it is not necessary that always the oscillatory means only 2 terms are there. There may be any number of times which is repeated after a certain time of interval. Then the series is oscillatory. Now it is the time for fundamental theorem on infinite series. So what this fundamental theorem says? Fundamental theorem says that addition or deletion of a finite number of terms does not affect the nature of the infinite series. So now, for example, if we consider a series 1, 2, 3, 4 in this way, it is up to infinity. Now, if we delete few terms from here, suppose we delete 1 and 2 from here. So, usually this series is a divergent series. After deletion of these two, we will find out it is still a divergent series. Not only that, instead of this deletion, if we insert some terms, suppose I insert here 5 times 1, 3 times 2. In this way, if I insert few terms, then also finally we will find out that the series is divergent. So insertion or deletion of terms in an infinite series will not affect its nature. So that is the fundamental theorem of infinite series. Now some properties of this infinite series. So the first property is the nature of an infinite series does not change by addition or deletion of a finite number of terms, which we will find out from the fundamental theorem. Moreover that by multiplication of all terms by a certain constant will not affect the property of the given series. So for example, if an is a convergent series and summation of an is equals to s, then if we multiply k with each term, then it is converging towards the value k into s, where k is a constant. So similarly, if it is a divergent series, then that value by multiplying the series by k will give the series is divergent only, whatever be the constant k. Now one more property, if summation an and summation bn are two series which are convergent and this converges towards the limit s1 and s2 respectively, then the series summation k1an plus k2bn is convergent, where k1 and k2 are constants. That is summation of, that is given that summation of an, that is this series is s1 and its converging value is s2, then this series if we want to construct, then it should converges towards k1 s1 plus k2 s2. So finally, if A and B, two series which are convergent, then this type of series if we construct by using the AN and BN, then this one is also the convergent series. And if they are divergent, then definitely these are also the divergent series. Not only that, among AN and BN, any one of them if it is divergent, then this type of series will finally be a divergent series. Now, it is the most important principle here, the Cauchy's general principle of convergence. This one is another principle by which we can find out a given series is convergent or not. So, at first, the statement for the principle. A sequence of real numbers an converges if and only if for every small epsilon greater than 0, there exists a number n such that mod of am plus p minus am less than epsilon for all m and p greater than n. So these are the m plus pth term and this is mth term. So if we take the difference of these two, then that value should be less than some epsilon value, which is a very small value. So that is for the sequence. The same thing we can apply for the series also. So if we require to apply this principle for the series, then what we will do, at first we find out the partial sum of the given series. After that, if the given series is converging to the value s, then its partial sum definitely converges to the value s. If and only if for epsilon greater than 0, there exists n belongs to n such that Sm plus p minus Sm less than epsilon for all m greater than n and p greater than 0. So just look, this is the m plus pth partial sum and this is the mth partial sum. If we take the difference of these two, then if we can show that this difference is less than epsilon, a very small quantity, for any m, for all m greater than equals to m and definitely p value is greater than 0, then we can say the series is convergent. Otherwise, series is not convergent. One thing we should note for here that this Cauchy's principle has the advantage that one need not know the limit L in order to demonstrate its convergence. Previously what happened? We should know the limit L, then only we can demonstrate with this example, that with this definition. But here, if you don't know the limiting value, then also we can demonstrate this one or we can find out our conclusion. So just let us do with an example. So prove by using Cauchy's criteria that the series summation of 1 upon n factorial is convergent. So how to prove that by using the Cauchy's general principle of convergence? So for that, first of all, we should find out the m plus pth partial sum and the mth partial sum for the given series. So given series is 1 upon n factorial. So here, if we take the corresponding term with summation, with this subtraction, then definitely m plus 1th term onwards, the term will be left and up to m plus pth term we will find out. So if we do this subtraction, then the remaining terms are 1 by m plus 1 factorial plus 1 by m plus 2 factorial. In this way it is up to 1 by m plus p factorial. Now that definitely we can say it is less than 1 by 2 to the power m. Here just look, it is 1 by m plus 1 its factorial. So that means it is starting from 1, 2, 3, 4. In this way it is m plus 1. Now if we just replace this value by 2 to the power n, then it is very true that 1 by m plus 1 factorial is less than of 1 by 2 to the power m. Likewise, if we replace all those corresponding to the increasing power of 2, then we will replace this entire series in this format. So this one, from if we take 1 by 2 to the power m common, then the remaining part is a GP series where the number of terms are p. So on that respect, here the common ratio is half, which is less than 1. So if we just apply the formula for the summation, then this is the formula, and after simplification we will find out here that it is less than 2 into 1 upon 2 to the power m for whatever be the value of p. So now it is 1 by 2 to the power m tends to 0 as m tends to infinity. For each epsilon greater than 0, there exists n depending on epsilon, for which this particular term we can say it is less than epsilon. So we can finally write that this mod value Sm plus p minus Sm is less than epsilon whenever n greater than n capital N and p greater than equals to 1. Hence the given series is convergent by Cauchy's criterion. So in this way we can verify that the given series is convergent or not. Likewise, you may try so many series to find out the series is convergent or not. Now this is the end of this video, and in the next video we will going to consider the series of positive terms. So till that, have a nice day and thank you.